A planet 13 times wider than Jupiter floats in the darkness of deep space. It sits 5,700 light-years from Earth, drifting through the constellation Cygnus. Scientists discovered it in 2016 and immediately knew something was wrong. This object breaks every rule we have for how planets form. It orbits a dying red giant star that should have swallowed it whole millions of years ago. The planet survived by pure cosmic chance, expanding to impossible size as its star aged. Astronomers named it ROX S 42b, but its nickname tells the real story: the monster planet. It contains enough mass to crush 13 Jupiters into a single sphere. Surface temperatures reach 1,800 degrees, hot enough to vaporize iron. This is not just the largest planet we have ever found, as it represents the absolute limit of what physics allows a planet to become. One step larger, and it would ignite into a star. Scientists now believe dozens more of these giants hide in the darkness between stars, waiting to be discovered. If you find this fascinating, hit that like button and subscribe. We begin now. Stand on Earth and look up. The sky stretches above you, deeper than you can measure with your eyes alone. Our planet measures 7,926 miles across. That's wide enough that if you started walking in a straight line, it would take you about a year of non-stop walking to circle back to where you started. A year of footsteps, just to trace the circumference of the rock beneath your feet. The moon floats 238,855 miles away. A light crosses that distance in 1.3 seconds. One heartbeat, one blink. But if you could drive there at highway speed, never stopping for gas or sleep, the trip would take about 5 months. 5 months of nothing but road, stretching through empty space. And that's just the moon, our closest neighbor in the cosmic dark. Mars comes closer to us sometimes. At its nearest approach, the red planet sits 34 million miles away. Light from the sun takes 8 minutes to reach Earth. 8 minutes of pure speed, crossing 93 million miles of space before warming your skin. The time it takes light to cross your living room is immeasurably fast. So fast, it might as well be instant. But there's a star in the night sky called Betelgeuse. It sits 500 light-years away. 100. And that's 2.94 quadrillion miles. If you started walking toward Betelgeuse when the pyramids were built and walked every single day without stopping, you would only be 0.0001% of the way there. 4,500 years of walking. Every step your ancestors took, every footprint in the sand, and you wouldn't even register as having moved. Light from Betelgeuse takes 500 years to reach your eye. 500 years of travel at 186,282 miles per second. The photons hitting your retina right now began their journey 500 years ago. Columbus hadn't sailed yet. The printing press was brand new. You're not seeing Betelgeuse as it is. You're seeing what it was when the Renaissance was just beginning. Light isn't just distance, it's time. And right now, you're looking backward through 5 centuries. This is the part that gets me. The universe doesn't show us the present, it shows us the past. Every star you see in the night sky exists in its own time pocket, sending light across distances so vast that the star itself might already be dead. The light keeps traveling anyway, crossing the void, carrying the image of something that no longer exists. From the moon, Earth looks like a pale blue pixel on a screen the size of a continent. Visible, but you'd have to squint. Our entire world compresses into a single dot of color against the black. All the oceans and mountains and cities and 7 billion people reduced to one tiny speck of light. That's what distance does. It erases detail. It turns complexity into simplicity. Mars sees us as even less. Yes, a faint blue star in its sky, no different from the thousands of other stars scattered across the dark. From Betelgeuse, if anyone were there to look, Earth wouldn't exist at all, not even as a pixel. The sun would be just another star, unremarkable, lost in the crowd of billions. The time it takes light to reach Betelgeuse is longer than the printing press has existed, longer than the United States has been a country, longer than most human institutions have survived. If you sent a message to Betelgeuse today, traveling at light speed, It wouldn't arrive until the year 2524, and if someone there sent a reply immediately, you wouldn't receive it until the year 3024. A 1,000-year conversation. One question, one answer. That's it. Distance isn't just space, it's isolation. And it's the universe saying, this is how far apart things really are. This is how long everything takes. The light crossing your eye right now left Betelgeuse during the Renaissance. Before the telescope was invented. Before anyone knew what a star actually was. We're not looking at Betelgeuse, we're looking at its past. A ghost image of something that might have already changed completely. Or ended. We won't know for another 500 years. Think about what that means. The universe you see doesn't exist. Not as you're seeing it. Every point of light in the night sky is out of sync with every other point of light. Some are showing you images from 100 years ago, some from 1,000, some from millions. The sky is a patchwork of different moments, all pretending to be the same present. You're standing on Earth, 7,926 miles wide, looking up at a star 500 light years away. And between you and that star, there's almost nothing, just empty space. Darkness so complete it has no temperature, no sound, no reference point. Light crosses it for centuries before reaching anything solid. But to understand why Betelgeuse matters, we need to understand what it actually is. Betelgeuse isn't just a light source 500 light years away. It's a star, a red supergiant star, one of the largest known objects in the observable universe. And it's dying. You can see it without a telescope, without binoculars. Step outside on a winter night. Look for Orion, the 3 stars that make his belt, the 4 that frame his shoulders and feet. One of those corner stars glows reddish-orange. That's Betelgeuse, the left shoulder of the hunter. It's been there in human mythology for thousands of years. Ancient Egyptians saw it. Medieval sailors navigated by it. Your great-grandparents looked at the same point of light. But here's what they didn't know, what nobody knew until recently. Betelgeuse is approximately 700 million miles across. 700 million. If you tried to count every breath you'll take in your entire lifetime, roughly 600 million breaths from birth to death, you'd barely equal the number of miles across this single star. One star. Wider than all the air that will ever pass through your lungs. Let's put that another way. The Sun is 864,000 miles wide, big enough to fit 1 million Earths inside. That's the Sun, the thing that lights and heats our entire world. Betelgeuse is 900 to 1,000 times larger. If the Sun were a marble sitting on a table in front of you, Betelgeuse would be a yoga ball 10 blocks away. Not just bigger, incomprehensibly bigger. The scale doesn't fit in your head. It doesn't fit in anyone's head. And here's where it gets strange. Betelgeuse is cooler than the Sun. The Sun's surface burns at 5,778 Kelvin, hot enough to melt any material we know. Betelgeuse sits at 3,500 Kelvin, almost half the temperature. That's why it's red. The color we associate with heat, with fire, with danger, is actually the color of stars that are cooling down, dying. Our intuition about temperature is backward in space. Red stars are the coolest stars you can see with your naked eye. Blue stars are the hottest. Everything we learned from stoves and flame is reversed out there. But cooler doesn't mean dimmer. Betelgeuse is 100,000 times more luminous than the Sun. 100,000. It's like comparing a dim floodlight to a bright flashlight. The flashlight is hotter, more intense up close, but the floodlight fills an entire stadium. Betelgeuse compensates for its lower temperature with sheer size. All that surface area radiating light, even from 500 light years away, even after centuries of traveling through empty space, its light reaches us as one of the brightest stars in the night sky. Think about what that means for a second. A star cooler than the Sun, outshining it by a factor of 100,000. Size isn't just a number, it's a different category of existence. Betelgeuse isn't a bigger version of the Sun, it's something else entirely. A different kind of object, playing by different rules. Red supergiants are rare. There are maybe a few hundred in our entire galaxy. Maybe. Most stars never reach this stage. They don't have enough mass. They burn steadily for billions of years, then fade quietly. But stars like Betelgeuse, stars born with more than 8 times the Sun's mass, they take a different path. They burn fast, burn bright, expand to enormous sizes, and then they explode. Betelgeuse is near the end. Astronomers estimate it could go supernova anytime in the next 100,000 years. Could be tomorrow, could be 50,000 years from now. In cosmic terms, that's the blink of an eye. The star is unstable. Its outer layers pulse and heave. Sometimes it dims by half its normal brightness. Sometimes it brightens. The whole structure is wobbling, convulsing, running out of fuel. Here's the thing that keeps astronomers up at night. Betelgeuse is 500 light-years away, the light we see left during the Renaissance. If Betelgeuse exploded 400 years ago, we wouldn't know yet. The explosion would still be traveling toward us, racing across empty space. We might be looking at a star that's already gone, already scattered its guts across the cosmos, and we're still seeing its ghost, still watching it twinkle peacefully in Orion's shoulder. When it does explode, if it hasn't already, it will be visible during the day, bright enough to cast shadows at noon, bright enough to read by at midnight. It will outshine the full moon, and the explosion will be visible for months, maybe years. Every human on Earth will see it, and then it will fade, and Orion will have a missing shoulder. The constellation that has guided sailors and marked the seasons for all of human history will look different, permanently. But supernovas aren't just bright. They're not just spectacles. They're foundational events. They're how the universe creates everything that isn't hydrogen and helium, the calcium in your bones, the iron in your blood, the oxygen you're breathing right now. All of it came from stars like Betelgeuse, stars that grew massive, fused heavier and heavier elements in their cores, and then exploded, seeding space with the raw materials for planets, for life, for you. Betelgeuse is a factory, has been for millions of years, building elements, stacking atoms, creating complexity out of simplicity. And when it finally runs out of fuel, when the fusion stops and gravity wins, it will share everything it made, violently, beautifully, one last act of creation through destruction. That's what we're looking at when we see that reddish star in Orion. Not just a light, not just a distance, a dying giant, a cosmic foundry, a future supernova, waiting. What does it mean for a star to die? Not fade, not go dark, die. Stars don't just switch off. They don't run out of light the way a bulb burns out. They transform. They exhaust themselves. They collapse under their own weight, and then they detonate. The death of a star is violent. It's fast. And for a star like Betelgeuse, it's close. Let's walk through it. The whole arc, birth to explosion. Stars form from clouds of gas and dust floating in space. These clouds are cold, thin, mostly hydrogen. Gravity pulls them together, slowly at first, then faster. The cloud collapses inward. As it collapses, it heats up. Pressure builds, temperature rises. Eventually, the core gets hot enough that hydrogen atoms start fusing together. They become helium. That fusion releases energy, tremendous energy, enough to push back against gravity. The collapse stops. The star ignites. This is the main sequence. The long, steady burn. Our sun is in this phase right now. Has been for about 4.5 billion years. Will be for another 5 billion. The main sequence is stable, predictable. Hydrogen fuses into helium in the core. Light and heat radiate outward. Gravity pulls in. Pressure pushes out. The forces balance. And the star just sits there, burning. Picture a bonfire. You stack logs in the fire pit. You light it. For hours, those logs burn steadily. The flames stay consistent. The heat is constant. You sit around it, watching the embers glow. That's the main sequence. The long night, the slow consumption of fuel. But eventually, the hydrogen runs out. Not all of it, just the hydrogen in the core, the center of the star. That's where the pressure and temperature are high enough for fusion. When the core runs out of hydrogen, fusion stops. The energy pushing outward disappears. Gravity wins. The core contracts. As it contracts, it heats up, gets denser, hotter, hot enough that helium starts fusing. Helium fuses into carbon and oxygen. That releases energy again, pushes back. But here's the thing. When helium fusion starts, the outer layers of the star don't contract. They expand massively. The core is burning hotter than ever, producing more energy than the hydrogen ever did. That energy pushes the outer layers outward. The star swells, grows, becomes a red giant. Or for really massive stars, a red supergiant. The surface cools as it expands. The star turns red, but it's bigger, so much bigger. It produces more total light than it ever did on the main sequence. This is the bonfire's final act. You've burned through the logs, the fire is dying, so you start throwing on everything else. Cardboard, scraps of wood, old furniture, anything that burns. The flames flare up, bright and hot, chaotic, beautiful, but you know it's almost over. You can feel it. This isn't the steady burn anymore. This is desperation. For a star like our sun, and this is where the story ends. The sun will expand into a red giant, swallow Mercury, maybe Venus, maybe Earth. Then it will shed its outer layers into space. The core will remain, a white dwarf, a dense, cooling ember. That's it. But for massive stars, the process continues. Helium runs out. The core contracts again, heats up again. Carbon starts fusing. Carbon fuses into neon and magnesium. Then neon runs out. The core contracts. Neon fuses into oxygen. Then oxygen runs out. Oxygen fuses into silicon. Each stage is shorter than the last. Hydrogen fusion lasts billions of years. Helium fusion lasts millions. Carbon fusion lasts thousands. Oxygen fusion lasts about a year. Silicon fusion lasts 1 day, 1 Earth day, 24 hours. Betelgeuse has been alive for about 8 to 9 million years, and it's been a red supergiant for roughly 40,000 years. Right now, at this moment, its core is fusing silicon into iron. It has 24 hours of fuel left, not metaphorically, literally. After millions of years of burning, after swelling to a size that defies comprehension, Betelgeuse is down to its last day. It's not dying. It's already dead. It just doesn't know it yet. Iron is the end of the road. You can fuse elements lighter than iron and get energy out. That's what stars do. That's what keeps them alive. But iron is different. Fusing iron doesn't release energy. It consumes energy. Iron is stable. It doesn't want to fuse. It can't be used as fuel. When the core fills with iron, fusion stops. Completely. The core is now just sitting there. A ball of iron roughly the size of Earth. No fusion, no energy, and no outward pressure. Just gravity. And gravity doesn't wait. The core collapses. It happens faster than you can say the word collapse. In a quarter of a second, a sphere the size of Earth compresses to the size of Manhattan. The density becomes unimaginable. Electrons are forced into protons. They become neutrons. The core becomes a neutron star, a ball of neutrons so dense that a teaspoon would weigh as much as a mountain. The collapse stops abruptly. The core can't compress any further. It rebounds. That rebound sends a shockwave outward, through the iron core, through the silicon layer, through oxygen, neon, carbon, helium, through the entire star. The shockwave moves at a significant fraction of the speed of light. It obliterates everything in its path. The star explodes. Supernova. And the outer layers are ejected into space. The core remains a neutron star, or if the star is massive enough, a black hole. The explosion releases more energy in a few seconds than the star produced in its entire lifetime. It outshines the galaxy for weeks, for months. This is what's waiting for Betelgeuse. The silicon is almost gone. The iron core is growing. The clock is ticking. When the core reaches a critical mass, about 1.5 times the mass of the Sun, it will collapse. The supernova will begin, and we will see it. Here's the thing though, Betelgeuse might have already exploded. The light from that explosion could be traveling toward us right now. Betelgeuse is 640 light-years away. That means the light we see tonight left Betelgeuse 640 years ago, around the time of the Renaissance. If Betelgeuse exploded yesterday, we won't know for another 640 years. If it exploded 300 years ago, The light is halfway here. We won't know until the light arrives, and when it does, it will be bright enough to cast shadows at night for weeks, maybe months. We could wake up tomorrow to 2 suns in the sky, one of them real, one of them already gone. Just the echo of a star that died centuries ago, finally reaching our eyes. That's what we're watching. That's what we're waiting for. A giant in its final act, a core collapsing in silence, a shockwave already tearing through layers of fusing gas. Or maybe none of that has happened yet. Maybe Betelgeuse is still there, still burning silicon, still holding on. We don't know. We won't know. Not until the light arrives. But what keeps a star from collapsing under its own weight? That's the question. Because a star is mass, enormous mass, all of it pulling inward. Gravity doesn't care that you're made of hydrogen. It doesn't care that you're burning. Gravity just pulls. Every atom in a star wants to fall toward the center. The sun has 200 million trillion kilograms of matter, all of it being pulled inward at every moment. That's more mass than 1 million Earths. Every gram of it wants to collapse, but it doesn't. The reason is fusion. Deep in the core, hydrogen atoms are crushed together so violently they merge into helium. That process releases energy, a lot of energy. Photons, heat, radiation, all of it screaming outward from the core, pushing against the layers above. And that outward pressure is the only thing holding the star up, the only thing keeping it from collapsing into a point. This balance has a name: hydrostatic equilibrium. Gravity pulls in, fusion pushes out. The forces are equal. The star stays stable. Imagine holding up a skyscraper with your thumb. That's what fusion does. It holds up the crushing weight of a star's outer layers with nothing but the pressure from exploding atoms. The moment fusion stops, the skyscraper falls. There's no gradual lean, no slow tilt. It just drops. Hydrostatic equilibrium is like a tug of war where both sides are equally matched. Gravity pulls inward. Fusion pushes outward. The rope doesn't move. But the moment one side lets go, even for an instant, the other side wins completely. There's no slow collapse. It's instant. The sun is in perfect equilibrium right now. It has been for 4.5 billion years. It will be for another 5 billion. Every second, the core fuses 620 million tons of hydrogen into helium. That fusion releases enough energy to keep the sun inflated, to keep it from collapsing. But fusion has a cost. The sun converts 4 million tons of matter into energy every second just to stay inflated. 4 million tons every second. That's the price of stability. That's roughly the mass of 1,000 semi-trucks, vanishing into pure energy every single second just to prevent collapse. If the sun stopped paying that price, even for a moment, gravity would win. Here's the thing about equilibrium. It's not passive. It's not the star sitting quietly in space, content and still. Equilibrium is violent. The star is exploding from the inside, constantly. Fusion is a continuous detonation, a bomb that never stops going off. The only reason the star doesn't blow apart is because gravity is crushing it inward just as hard. The star isn't stable because it's calm. It's stable because 2 catastrophic forces are perfectly matched. Think about that. The sun is only here, only this size, only this shape, because it's in a constant state of barely controlled explosion. If fusion weakened even slightly, gravity would crush the core tighter, which would make fusion burn hotter, which would push back harder. The system corrects itself. It finds balance. That's why stars can burn for billions of years without flickering. But equilibrium isn't permanent. Betelgeuse is losing its balance. Remember, it's fusing silicon in the core. Now, silicon fusion produces iron. Iron doesn't fuse. It can't. Fusing iron takes more energy than it releases. So when the core turns to iron, fusion stops. No fusion means no outward pressure, and no outward pressure means nothing is holding up the star. When that moment comes, when the last silicon atom fuses into iron, the core collapses. Not over hours, not over minutes. In about 1/4 of a second, the core implodes. Gravity wins. The entire core, an object roughly the size of Earth, compresses down to something the size of a city. in less than a second. And the speed is hard to imagine. The outer layers of the core are falling inward at 70,000 kilometers per second. That's almost 1/4 the speed of light. The collapse stops only when the core becomes so dense that the atoms themselves can't be crushed any further. The core rebounds. That rebound sends a shockwave outward. The shockwave hits the infalling outer layers, and the star explodes. That's the pattern. Equilibrium, then collapse, then explosion. Every massive star follows it. Fusion ends. Gravity wins. The star dies. Here's the surprise. If the sun's fusion stopped right now, we wouldn't know for 8 minutes. That's the time it takes light to reach Earth. We'd keep seeing the sun, bright and normal, for 8 more minutes. But the sun itself would collapse almost immediately. No fusion means no pressure. Gravity would crush the core. The outer layers would fall inward. Within about 27 minutes, the sun would shrink from a sphere over 1 million kilometers wide to a sphere about the size of Earth. Not hours, not days, half an hour, and the sun would be a white dwarf, a dense, cooling ember where a star used to be. 27 minutes. That's how long equilibrium matters. That's how fast gravity wins when fusion stops. The sun won't do that, of course. It doesn't have enough mass to collapse that way. When the sun's fusion ends, billions of years from now, it will shed its outer layers gently and leave behind a white dwarf. No collapse, no shockwave, just a slow fade. But massive stars don't get that option. They're too big. Gravity is too strong. When their fusion stops, collapse is instant. A Betelgeuse is in the final stage of equilibrium. Each fusion process produces less outward pressure than the last. Hydrogen fusion held the star up for millions of years. Helium fusion for less. Carbon, neon, oxygen, silicon. Each stage burns faster. Each stage produces less pressure. The core is shrinking. Gravity is winning. Slowly, step by step. Silicon fusion might last a few days, maybe a week, then iron, then collapse. Every star is locked in this battle. Gravity versus fusion. Collapse versus explosion. The stable stars, the ones burning hydrogen quietly for billions of years, they're not peaceful. They're at war. They're just winning. The balance holds. The equilibrium lasts. But equilibrium isn't the only thing that determines a star's fate. There's also the question of what the star leaves behind. The sun is different. It's not racing toward collapse like Betelgeuse. It's not burning through fuel in a desperate final sprint. The sun is stable. It's been stable for about 4.5 billion years, and it will stay stable for another 5 billion more. That stability comes from equilibrium, gravity pulling inward, fusion pushing outward. The forces balance. But that doesn't mean the sun is simple. Let's talk about what the sun actually is, what it's made of, what's happening inside it right now. The sun is 73% hydrogen by mass, 25% helium. The remaining 2% is everything else: carbon, oxygen, iron, trace amounts of heavier elements. All of it compressed into a sphere 109 times wider than Earth. Most of that mass is squeezed into the core. And that's where the real work happens. The core of the sun is 15 million Kelvin. That's about 27 million degrees Fahrenheit, if you need the comparison. The pressure at the core is 250 billion atmospheres, 250 billion times the air pressure you're feeling on your skin right now. At that temperature and pressure, hydrogen atoms don't just sit there. They collide. They fuse. 4 hydrogen nuclei combine to form 1 helium nucleus. That process releases energy, a lot of energy. The sun fuses 600 million tons of hydrogen into helium every single second. 600 million tons per second. That's hard to picture. Think of it this way. Every second, the sun converts about 3.5 times the mass of all the water in Lake Superior into helium. Every second. The process never stops. A day and night don't mean anything to the sun. It's always on, always fusing, always burning. But here's the thing. When hydrogen fuses into helium, the helium weighs slightly less than the hydrogen that went into it. The missing mass doesn't just disappear. It becomes energy. E equals mc squared, Einstein's equation. That tiny difference in mass, multiplied by the speed of light squared, becomes the light and heat we feel from 93 million miles away. The Sun loses 4 million tons of mass every second as pure energy. 4 million tons. That sounds catastrophic, but the Sun weighs about 2 times 10 to the power of 30 kilograms. That's 2,000 trillion kilograms, if you want to say it out loud. Losing 4 million tons per second barely touches that total. Over the Sun's entire lifetime so far, about 4.5 billion years, it's lost roughly 0.03% of its mass. That's equivalent to about 100 Earths. 100 Earths sounds like a lot, but compared to the Sun's total mass, it's nothing. The Sun loses mass equivalent to all of Earth's oceans every 150 million years. That's 0.02% of its total mass. It's like losing a single eyelash every decade. You'd never notice. The energy created in the core doesn't just shoot out into space. It has to escape first. That takes time. The Sun has layers. The core is where fusion happens. Outside the core is the radiation zone. The radiation zone is thick, dense, packed with particles. Photons created in the core try to move outward, but they can't travel in a straight line. They collide with particles. They bounce, and they scatter. They get absorbed and re-emitted, over and over, trillions of times. A photon created in the Sun's core will take about 170,000 years to reach the surface. 170,000 years. Actually, that's not quite right. Let me try again. It's not that the photon is moving slowly. Photons always move at the speed of light, but the path isn't straight. It's like trying to walk through a crowd where every person is packed shoulder to shoulder, and you can only move 1 inch per collision. You'd bounce off one person, then another, then another. You'd zigzag, you'd backtrack. Crossing a city would take you thousands of lifetimes. That's what happens inside the Sun. The photon bounces so many times that even though it's moving at light speed, it takes 170,000 years to escape. And think about that. The sunlight hitting your face right now was created 170,000 years ago. The photons are old. They were born in the core when Neanderthals still walked the Earth. They've been trapped inside the Sun, bouncing and scattering until this moment. You're not feeling the Sun's current energy. You're feeling its deep past. The fusion happening in the core right now won't reach you until the year 172,000 AD. You'll never see it. Neither will your children. Neither will anyone alive today. The core itself is almost unimaginable. The density is about 150 times the density of water. That doesn't sound too extreme, but the temperature and radiation make it lethal in ways that go beyond normal danger. A pinhead of core material, and if you could somehow extract it and place it on Earth, would kill you from 150 kilometers away. Not from heat, from radiation. You wouldn't even see it. You wouldn't feel warmth. You'd just stop existing. Your cells would unravel. The bonds holding your molecules together would break. Distance wouldn't save you. Radiation doesn't care about proximity the way heat does. The Sun's core produces about 276 watts per cubic meter. That's less than a car engine. Less than your body produces per cubic meter when you're exercising. The Sun isn't hot because the core is producing insane amounts of energy per unit volume. It's hot because there's so much core, so much mass packed into such a small space. The total energy output is enormous because the volume is enormous. At 386 billion megawatts. That number doesn't mean much until you realize it's more energy than humanity has used in its entire existence, released every single second. The fusion process is delicate. It requires precision. The temperature has to be high enough for hydrogen nuclei to overcome their electromagnetic repulsion. They're both positively charged. They want to push away from each other. Only at 15 million Kelvin do they move fast enough to collide and stick. The pressure has to be high enough to keep the particles close together. Without gravity compressing the core, fusion would stop. The Sun would cool. The light would fade. Equilibrium would collapse. The Sun has been losing mass for 4.5 billion years. It will keep losing mass for another 5 billion. The process is slow, a steady, predictable. Stars like the Sun don't change quickly. They don't suddenly flare up or collapse. They burn through their fuel at a measured pace. Hydrogen becomes helium. Helium accumulates in the core. The core grows denser. The temperature rises slightly. The fusion rate increases. But these changes take millions of years, billions of years. You can't see them in a human lifetime. You can't even see them in 1,000 human lifetimes. That stability is what makes life possible. Earth has been in the habitable zone for billions of years because the Sun's output hasn't changed dramatically. The light we receive today is almost identical to the light that warmed the oceans when the first cells appeared. Stars like the Sun are predictable. They follow a pattern. They burn hydrogen for 10 billion years, and then helium for a fraction of that. Then they die. The timeline is set by mass, by composition, by the laws of physics. But the Sun's stability doesn't mean the solar system has always been this way. In fact, the planets haven't always been where they are now. The Sun's stability doesn't mean the solar system has always been this way. The planets we see today are not in their original positions. They moved. They migrated. Some were destroyed entirely. Planetary systems begin as protoplanetary disks, clouds of gas and dust orbiting young stars. The dust clumps together. Pebbles become boulders. Boulders become planetesimals. Planetesimals collide and merge into planets. The process takes millions of years. But once planets form, they don't just stay put. Planets interact with each other through gravity. A large planet pulls on a smaller one. The smaller planet's orbit shifts, sometimes inward, sometimes outward. The gas giants especially reshape the system. Jupiter and Saturn are so massive that their gravitational influence extends across billions of miles. They nudge other planets, they scatter debris, they rearrange the architecture of the entire solar system. Think of planetary formation like a game of musical chairs, where the chairs are moving, the music never stops, and some players get thrown out of the room entirely. The planets we see now are the ones that found stable chairs, the ones that didn't collide with each other, the ones that didn't spiral into the Sun, the ones that didn't get flung into interstellar space. Every stable system is a survivor. Our solar system went through this chaos. And the arrangement we have now is not the arrangement we started with. Scientists call this the nice model, named after the French city where it was developed. The model suggests that Jupiter, Saturn, Uranus, and Neptune formed much closer together than they are today. They were packed into a tighter region, closer to the Sun. Over hundreds of millions of years, gravitational interactions pushed them outward. Saturn drifted away from Jupiter. Uranus and Neptune migrated even farther. The migration wasn't smooth. It was violent. When the gas giants moved, they destabilized everything around them. Asteroids and comets got caught in their gravitational fields. Some were hurled inward toward the inner planets. Some were ejected completely. The late heavy bombardment, and a period about 4 billion years ago when the inner planets were pummeled by impacts, was likely caused by this migration. The Moon's craters, Mars' battered surface, Earth's scarred history, all consequences of planets rearranging themselves. Jupiter's migration was especially dramatic. The Grand Tack hypothesis suggests that Jupiter didn't just move outward, it moved inward first. Early in the solar system's history, Jupiter may have migrated all the way down to where Mars is now. Then, Saturn formed. Saturn's gravity interacted with Jupiter's. The two planets locked into a resonance, and that resonance reversed Jupiter's migration. It pulled Jupiter back outward, away from the inner solar system. Jupiter migrating inward and then outward is like a wrecking ball swinging through the inner solar system. Anything in its path either got flung into the Sun or ejected into interstellar space. Earth survived by luck. If Jupiter had continued inward, Earth might not exist. If Jupiter had moved outward earlier, Earth's orbit could have been destabilized. We're here because the timing worked out, because Saturn formed at the right moment, because the resonance kicked in before Jupiter destroyed everything. Not all planets are so lucky. Planetary migration ejects planets from their systems entirely. They become rogue planets, worlds drifting through interstellar space with no star to orbit, no light, no heat, just the faint glow of residual warmth from their formation. Astronomers estimate there could be billions of rogue planets in the Milky Way alone, more rogue planets than stars, and most were likely ejected during the chaotic early years of their systems. They're the ones who didn't find a stable chair, and some planets don't get ejected. They spiral inward, toward their star. The process is slow. The planet's orbit decays over millions of years. Its atmosphere gets stripped away by stellar wind. It heats up. Eventually, it crosses the star's surface. When a star consumes a planet, it's not dramatic. The planet spirals inward over millions of years, shedding atmosphere, until it finally crosses the star's surface and dissolves like a snowflake, drifting toward a blast furnace. The star doesn't explode. It doesn't brighten suddenly. The planet just disappears, vaporized, mixed into the star's outer layers, gone. Here's the unsettling part. 1 in 5 sun-like stars has eaten its own planets. And we know this because their atmospheres contain unusual amounts of lithium and other heavy elements, the digested remains of worlds that no longer exist. Lithium is destroyed quickly in stars. It burns up in nuclear reactions. If a star has a lot of lithium in its atmosphere, it didn't come from the star itself. It came from something the star consumed. A planet, maybe several planets. 20 to 35% of sun-like stars show evidence of this. Chemical signatures that shouldn't be there, elements too heavy to form in a star's outer layers. They had to come from somewhere else, from planets that spiraled inward, from worlds that no longer orbit their stars because they became part of their stars. Our sun might have eaten planets too. We'd never know unless we compared its composition to other stars. If the sun consumed a planet billions of years ago, the evidence would still be there. Trace amounts of lithium, heavier elements mixed into the photosphere, but we can't tell if those elements were there from the start or if they came from a planet. The sun's composition looks normal compared to other stars, but normal doesn't mean innocent. It just means we can't prove anything. The solar system's current stability is the result of billions of years of chaotic sorting. The planets we see are the survivors. They found orbits that don't intersect. They reached a configuration where their gravitational influences balance out. The system is stable now, but it wasn't always. It won't be forever. In a few billion years, when the sun becomes a red giant, the inner planets will be consumed. Mercury first, then Venus, possibly Earth, and the outer planets will survive, but their orbits will shift again as the sun loses mass. The stability we experience is temporary, a snapshot of a system in transition. Planetary systems are not permanent. They're not fixed. They're dynamic. They evolve. They destroy themselves and rebuild. Most systems probably look nothing like they did when they formed. The planets moved. The debris got cleared out. The survivors settled into whatever orbits allowed them to coexist. Our solar system is one outcome among countless possibilities. One arrangement that happened to work. One configuration where a rocky planet ended up at the right distance from its star. Where gas giants migrated outward instead of inward. Where nothing catastrophic happened for long enough that life could take hold. But not all planets orbit alone. Some exist in systems so strange that they challenge our definitions. Some exist in systems so strange they redefine what we thought a planet could be. For most of human history, we knew 8 planets. 9, if you count Pluto before the demotion. They all followed certain rules. Rocky planets close to the sun, gas giants farther out, orbits roughly circular, everything spinning in the same direction. We assumed that's just how planetary systems worked. Then we found the exoplanets, thousands of them, and almost none of them followed our rules. The first category that broke our expectations, hot Jupiters. These are gas giants orbiting closer to their stars than Mercury orbits the sun. Mercury is already close, 36 million miles out. Surface temperatures hit 430 degrees Celsius during the day. That's hot enough to melt lead. Hot Jupiters orbit even closer. Some complete an orbit in less than 4 Earth days. Their dayside temperatures exceed 2000 Kelvin. That's around 3140 degrees Fahrenheit. Hot enough that rocks would glow red. Hot enough that metals vaporize. Take HD 189733b, a gas giant roughly the size of Jupiter. orbiting its star every 2.2 Earth days. The planet is tidally locked. One side always faces the star, one side trapped in eternal darkness. So the temperature difference between day and night is so extreme that winds scream across the Terminator at 5,400 miles per hour. That's 7 times the speed of sound. And it rains there, but not water, molten glass, silicate particles condensing in the upper atmosphere, falling sideways in those hypersonic winds. HD 189733b is so close to its star that its atmosphere is being stripped away in real time. It's like holding an ice cube above a blowtorch and watching it evaporate before it melts. The planet is slowly bleeding into space. In a few billion years, there might be nothing left but a molten core. We don't think hot Jupiters formed where we find them. Gas giants need to form farther out, where there's enough material. The leading theory is that they migrated inward. Gravitational interactions with other planets or the protoplanetary disk pushed them closer to their stars. Some probably fell all the way in, consumed. The ones we see are the survivors, locked in orbits where they're being slowly destroyed, but not yet dead. Then there are super-Earths, rocky planets larger than Earth but smaller than Neptune. We don't have anything like this in our solar system. Earth is the largest rocky planet we've got. Neptune is the smallest ice giant. There's nothing in between. But in other systems, super-Earths are common, maybe even the most common type of planet in the galaxy. Kepler 10c is 17 times Earth's mass. It's rocky, not a gas giant, not an ice giant. A ball of rock and metal 17 times more massive than our entire planet. Its gravity at the surface would be about 3 times what you experience standing here. You could still walk, just barely. Everything would weigh 3 times more, including you. That planet shouldn't exist according to our early models. Something that massive should have captured enough hydrogen and helium to become a gas giant. But it didn't. It stayed rocky. We had to revise our theories. Super-Earths raise questions about habitability. Some orbit in their star's habitable zone, the right distance for liquid water. But higher gravity means thicker atmospheres, different plate tectonics if they have plate tectonics at all, different weather patterns, different ocean currents. Life on a super-Earth, if it exists, would face challenges we've never considered. Then there are the rogue planets, planets that don't orbit stars at all. They were ejected from their systems during formation. Gravitational interactions with other planets or passing stars kicked them out. Now they drift through interstellar space, alone in the dark, orphans. We can't see rogue planets easily. They don't emit much light. They don't reflect light from a star because they're not near one. We only detect them when they pass in front of something brighter, causing a brief gravitational lensing event, or when we catch their faint infrared glow if they're still young and hot. Based on those detections, astronomers estimate there could be billions of rogue planets in the Milky Way. Maybe more. There may be more rogue planets in our galaxy than stars. Billions of worlds drifting in the dark and invisible unless they happen to pass in front of something brighter. Some of them may have been ejected from our own solar system billions of years ago. We might have had sibling planets we'll never meet. Here's the strange part. Some rogue planets might not be completely dead. If a rogue planet has moons, tidal heating could keep subsurface oceans liquid. The moon's orbit flexes the planet's interior, generating heat. No sunlight, no star, just the gravitational dance between a planet and its moon, keeping water liquid in the eternal night. Life could exist on a planet that has never seen a sun. We don't really know. That's the honest answer. We've never studied a rogue planet up close. We've only inferred their existence from fleeting shadows and distant glimmers. Not all planets orbit at reasonable distances. ROX S42b is a gas giant orbiting 157 billion miles from its star. That's 5 times the distance from the Sun to Pluto. Its year lasts 1,200 Earth years. If that planet had a civilization, they'd have no concept of seasons. Their entire recorded history would fit within a single orbit. Empires would rise and fall. Languages would be born and forgotten. And their star would barely move in the sky. Then There are planets in systems that shouldn't be stable. The TRAPPIST-1 system has 7 Earth-sized planets orbiting a white dwarf star. They're packed so tightly that all 7 orbits would fit inside Mercury's orbit around the Sun. Some of these planets are so close together that if you stood on one, the neighboring planet would appear larger in the sky than the Moon appears from Earth. Yet gravitational interactions between them are constant. Their orbits tug at each other. The system is stable for now, but it's a delicate balance. One perturbation and everything could collapse. These aren't planets from science fiction. They're real, detected, measured, catalogued. Every one of them challenges the neat categories we created based on our own solar system. We thought we understood what a planet was, a rocky ball or a gas giant, orbiting a star at a reasonable distance. But the universe doesn't care what we find convenient. Planets can be molten hellscapes with glass rain, rocky worlds 3 times more massive than anything in our system, drifters in the dark with no star to orbit, gas giants so far from their suns that they barely qualify as part of the system. And that diversity raises a question. If planets can be this different, what determines their size? What stops a planet from growing forever? The habitable zone. That's the term astronomers use for the region around a star where conditions allow liquid water to exist on a planet's surface. Not ice, not steam, liquid water. For our Sun, that zone currently stretches from about 0.95 to 1.37 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. Earth sits right at 1 astronomical unit. We're in the sweet spot. The habitable zone is like standing on a beach. Right now, you're at the perfect distance from the water. The waves lap gently at your feet. The temperature is comfortable, but the tide is coming in, slowly, over billions of years. Eventually, the ocean rises 93 million miles and drowns you. Stars change as they age. They get brighter, hotter. The nuclear fusion in their cores becomes more intense. As that happens, the habitable zone shifts outward, away from the star. The beach where you stand becomes ocean floor. The safe distance moves farther out. What was once too cold becomes just right. What was just right becomes too hot. Earth won't stay in the habitable zone forever. In about 1 billion years, the Sun will be roughly 10% brighter than it is today. 10% doesn't sound like much, but it's enough. Earth's surface temperature will rise past the point where liquid water can exist. The oceans will begin to evaporate. Water vapor will fill the atmosphere, trapping more heat, creating a runaway greenhouse effect. And within a few 100 million years after that, Earth will look like Venus, a scorched world with a thick, toxic atmosphere and surface temperatures hot enough to melt lead. 1 billion years. That's a long time by human standards. Life has existed on Earth for about 3.8 billion years. 1 billion years ago, the most complex life forms were algae and single-celled organisms. So there's time, but not infinite time. The pale blue pixel we talked about earlier has an expiration date. It's written into the physics of stellar evolution. There's no avoiding it. That's just the beginning. The real transformation comes in about 5 billion years. That's when the Sun will exhaust the hydrogen in its core and begin fusing helium. It will expand into a red giant. The outer layers will swell outward, are growing cooler but vastly larger. The Sun's surface will extend to roughly where Earth orbits now, maybe a little beyond. When the Sun becomes a red giant, it will expand beyond Earth's orbit. Earth might survive by spiraling outward as the Sun loses mass, or it might be consumed. It's like standing on train tracks, watching the train approach and hoping the tracks curve away at the last second. You won't know until it's too late. The surprise is this: Earth might not be consumed. As the Sun swells into a red giant, it will shed mass. The solar wind will carry away perhaps half of the Sun's total mass. When a star loses mass, its gravitational pull weakens. Planets in orbit respond by drifting outward, will spiral away from the expanding Sun, like a stone tied to a string that's slowly being let out. Some models suggest Earth will escape. The tracks will curve, the train will miss. But even if Earth survives, it won't be Earth anymore. By the time the Sun becomes a red giant, Earth will already have been a lifeless desert for 4 billion years. The oceans will be gone. The atmosphere will have been stripped away by solar wind. The surface will be geologically dead. No tectonic activity, no magnetic field. And if Earth does survive the red giant phase, it will end up as a scorched, airless rock orbiting a white dwarf. It might even become tidally locked, with one face permanently pointed toward the dying sun. It will be a fossil, a remnant of what it once was. The habitable zone during the red giant phase will shift outward dramatically. The zone where liquid water can exist will move to where Jupiter and Saturn orbit now, as somewhere around 5 to 10 astronomical units from the Sun. That's 5 to 10 times farther out than Earth. The moons of Jupiter and Saturn, currently frozen ice worlds, might briefly become warm enough for liquid water. Europa, Enceladus, Titan. For a few 100 million years, these moons could have oceans, lakes, rain. But the red giant phase doesn't last. The sun will shed its outer layers, leaving behind a white dwarf. The habitable zone will collapse inward again. Those brief oceans will freeze. The window will close. This isn't speculation. This is what happens to stars like the sun. We've observed thousands of red giants. We've mapped their sizes, their temperatures, their life cycles. We know what's coming, not just for the sun, but for every star in this mass range. Between about 0.8 and 8 solar masses, these stars become red giants. They consume or sterilize their inner planets. They shift their habitable zones outward. They die slowly, shedding their atmospheres into space. Betelgeuse has already gone through this process. It's a red supergiant now, but it was once a main sequence star, smaller and hotter than it is today. It almost certainly had planets, rocky worlds in close orbits, maybe gas giants farther out. We'll never know for sure. When Betelgeuse expanded, those planets were erased. The inner worlds were consumed outright, vaporized as the star's surface engulfed them. The outer planets might have survived the initial expansion, but they would have been baked by intense radiation, their atmospheres stripped away. Any moons they had would have been vaporized. Betelgeuse's expansion turned its planetary system into a graveyard. Now, when we look at Betelgeuse, we're not just seeing a dying star. We're seeing a graveyard. Any rocky worlds it had are gone. Any moons, vaporized. If there was ever life on one of those planets, no trace of it remains. Not a fossil, not a molecule, just the star itself, bloated and unstable, waiting to collapse. That's the fate of planetary systems around massive stars. They don't get billions of years of stability like we have. They get a few million years, maybe tens of millions, before their star expands and destroys everything. The habitable zone shifts so quickly that life, if it ever begins, barely has time to evolve past microbial stages. Then it's over. The star swells. The planets burn. The system dies. Our solar system will follow a gentler path. The sun's red giant phase will come slowly, over billions of years. But the outcome is the same. Earth, Mars, Venus, Mercury, all of them will either be consumed or left as lifeless husks. The habitable zone will shift outward briefly, then vanish when the sun becomes a white dwarf. The solar system will become a cold, dark place. The planets will still orbit, but they'll orbit a corpse. The universe doesn't preserve anything, not stars, not planets, not us. Everything that exists now will eventually be dismantled by time and physics. But Betelgeuse's size isn't just a number on a chart. To really understand it, we need to measure it against something we know. The diameter of Betelgeuse is roughly 700 million miles. That's the number astronomers give when they're being cautious. The star pulsates, so its size changes. Sometimes it's 640 million miles across. Sometimes it pushes toward 900 million. But let's use 700 million as our baseline. 700 million miles from one side to the other. That number doesn't mean anything yet. Not really. You need to measure it against something human, something you can feel. Let's say you decided to walk across Betelgeuse, just straight through, from one side to the other. You walk at 3 miles per hour, which is a normal walking pace. You never stop. You never sleep. You just walk. It would take you 26,500 years. Think about that. If you started walking when humans first started farming, when we built the first permanent settlements, you'd still be walking now. You wouldn't even be halfway. If you started before the pyramids were built, before writing was invented, before any civilization we know existed, you'd arrive just in time to watch our sun begin its red giant phase. The sun would be dying as you reach the other side. That's longer than all of recorded history. Every empire, every war, every discovery, all of it would rise and fall while you were still walking through a single star. Let's speed things up. Let's say you're driving instead. 60 miles per hour, highway speed, never stopping for gas, never pulling over, just driving straight through the star for 700 million miles. It would take you 1,330 years. You'd start your drive during the fall of Rome. You'd watch the Dark Ages pass outside your window, the Renaissance, the Industrial Revolution, 2 world wars, the invention of the car you're driving, the invention of the computer, the internet, smartphones. You'd arrive in the modern age, finally reaching the other side, and everyone you knew when you started would be dust. Even in a commercial airplane, flying at 500 miles per hour, it would take you 160 years. That's 2 full human lifetimes at cruising altitude. The fastest spacecraft humans have ever built is the Parker Solar Probe. It reached speeds of 430,000 miles per hour when it dove close to the sun. That's the fastest we've ever moved anything. At that speed, you could fly from New York to Los Angeles in less than a minute. You could circle Earth in 3 minutes. Crossing Betelgeuse at that speed would still take you 68 days, more than 2 months, in the fastest machine humanity has ever created. But here's where it gets strange. Light doesn't care about human speeds. Light moves at 186,282 miles per second. Nothing in the universe moves faster. Light crosses Earth's diameter in 0.04 seconds. A blink, less than a blink. Light takes 1 hour to cross Betelgeuse. 1 hour. The fastest thing that exists, the cosmic speed limit. The thing that crosses our entire planet in the time it takes you to snap your fingers, takes an hour to traverse this star. That's how wide it is. Betelgeuse is 90,000 times wider than Earth. 90,000 Earths, lined up side by side, would stretch from one edge of Betelgeuse to the other. The Sun is 109 times wider than Earth. We think of the Sun as enormous. We're right to think that. But Betelgeuse is 825 times wider than the Sun. Let's bring this closer to home. Let's put Betelgeuse where the Sun is. Just replace one with the other. What happens to the solar system? Mercury disappears instantly. It's not even close. Venus, gone. Earth, gone. Mars, gone. All of them would be inside the star, not orbiting it, inside it. The surface of Betelgeuse would extend past the orbit of Mars. It might reach Jupiter, depending on which estimate of Betelgeuse's size you trust. Earth wouldn't just be inside the star. We'd be deep inside. Our orbit would carry us through the outer layers of Betelgeuse, layers of plasma and radiation so hot they'd vaporize rock in seconds. The Moon would still be orbiting Earth, at least for a little while. Both bodies would still be locked in their gravitational dance. But they'd be surrounded by stellar material, plasma where space used to be. The Earth-Moon system would dissolve like sugar in boiling water. First, the atmospheres would burn away, then the surfaces would melt, then the molten material would disperse into the star's outer layers. Within hours, maybe less, there'd be nothing left. No trace that a planet and its moon had ever been there. Just more star. That's what size means at this scale. It's not about surface area or volume. It's about erasing the familiar. If Betelgeuse replaced the Sun, the inner solar system wouldn't exist anymore. There'd be no room for it. The star would occupy the space where 4 planets used to be. Jupiter might survive, barely, orbiting just outside the star's surface. Saturn, Uranus, Neptune would still be there, far enough out to avoid being swallowed. But they'd be orbiting a red giant instead of a yellow dwarf. The Sun's light is warm and steady. Betelgeuse's light is cooler, but vastly more intense. The outer planets would be bathed in red light, their surfaces heated to temperatures they've never known. The habitable zone would shift outward, somewhere past Jupiter. For a brief time, some of Jupiter's moons might be warm enough for liquid water. Europa, Ganymede. They'd have a few thousand years, maybe, before Betelgeuse's instability tore the system apart. But the inner solar system would be gone. Earth's orbit would be a path through fire. Mars would be a memory. The asteroid belt would be inside the star, countless rocks vaporized and absorbed. This is what it means to be 700 million miles across, and it means there's no space left for anything else. It means you don't orbit something that size. You're either far away or you're part of it. We measure stars in diameters. We compare them to Earth, to the Sun, to the distance between planets. Those comparisons help. They give us numbers to work with. But size is only one way to measure something. There's another way to understand Betelgeuse: by counting. Let's count something impossible. Betelgeuse has a volume 1.6 billion times the size of the Sun. The Sun has a volume 1.3 million times the size of Earth. Multiply those numbers together, and you get something hard to hold in your head. 2 quadrillion Earths. 2 million billion. That's how many Earths could fit inside Betelgeuse. Picture yourself counting them. 1 Earth per second. You start now, saying the numbers out loud. 1, 2, 3. You keep going. You don't sleep. You don't stop. You count for a minute, an hour, a day. After a year, you've counted 31.5 million Earths. You're not even close. After a century, you've counted 3 billion. Still not close. You'd need to count for 63 million years to reach 2 quadrillion. 63 million years ago, yes, the Cretaceous period was ending. Dinosaurs were dying. The asteroid had just hit. You'd start counting then. 1 Earth every second for the entire age of mammals, and you'd finish counting today. Every second that passes, Betelgeuse exists at that scale. Volume is one thing, energy is another. Betelgeuse radiates 100,000 times more light than the Sun. The Sun outputs 3.8 times 10 to the 26th joules every second. That number means nothing to you because it's too big. So let me try differently. Every second, the Sun releases more energy than humanity has used in its entire existence. Every power plant, every fire, every engine, every heartbeat that burned a calorie, all of it combined, across all of human history, and the Sun does that in about 1 second. Betelgeuse does it 100,000 times over, 4 times 10 to the 31st joules per second. It's been doing that for roughly 40,000 years, since before agriculture, since before civilization, since humans painted animals on cave walls in France. Betelgeuse has been pouring energy into the universe at a rate that makes the Sun look dim. That energy comes out as photons, particles of light. Betelgeuse emits roughly 10 to the 48th photons every second. Let me give you a number you can picture. There are about 200 billion stars in the Milky Way, maybe more. Multiply that by 10,000 galaxies. 2 quadrillion stars. Every one of those stars is a point of light, a source of photons, a furnace burning. Yet Betelgeuse emits more photons in 1 second than all of those stars combined are emitting right now, every second. It's not just bright, it's a photon factory running at a speed that makes the concept of bright feel inadequate. How do you describe something that redefines the scale? You use people. About 100 billion humans have ever lived. Every person who was born, lived, died. From the first Homo sapiens in Africa to the child born a moment ago. 100 billion lives. If every human who ever lived represented 1 photon, Betelgeuse would emit the entire human population of Earth 10 billion times over, in a single second. And it's been doing that for 40,000 years. Every second of every minute of every hour of every day since the last ice age. Betelgeuse has been producing light at a rate that turns human history into a rounding error. Think about your ancestors, your parents, their parents. Go back 10 generations and you have over 1,000 direct ancestors. Go back 100 generations, back to the Bronze Age, and the number climbs into the trillions. But those are just your human ancestors. Go further, back to the first primates, the first mammals, the first vertebrates, the first cells that learned to divide. If you count every organism in your direct lineage back to the beginning of life on Earth, you'd reach roughly 10 to the 15th individuals, a quadrillion ancestors. Every single one of them survived long enough to reproduce. Every single one of them is part of the chain that leads to you. Betelgeuse emits 1 billion times more photons than that every second. There's a measurement astronomers use called absolute magnitude. It's how bright a star would appear if you placed it exactly 10 parsecs away, about 32.5 light years. It's a standard distance, a way to compare stars without worrying about how far away they actually are. The Sun, at 10 parsecs, would have an absolute magnitude of 4.8. You could see it, but it wouldn't be impressive, just another star in the sky. Betelgeuse, at 10 parsecs, would have an absolute magnitude of -5.8. It would be brighter than the full moon. Not as bright, brighter. You could read by its light at midnight. It would cast shadows on the ground. You'd see those shadows move as the Earth turned. And a star 32 light years away would light up your bedroom like a nightlight you couldn't turn off. And Betelgeuse is not the brightest star in the universe. Not even close. It's just one of the largest. One red supergiant among thousands. There are stars more luminous. There are stars that make Betelgeuse look ordinary. We build these comparisons because numbers alone don't do the job. 2 quadrillion Earths, 10 to the 48th photons, 4 times 10 to the 31st joules. Those are accurate. They're true, but they don't connect. You can't feel them. You need something human, counting, ancestors, lifespans. You need touch passing, something happening, a story with a beginning and an end. Even then, the numbers fight back. They resist being understood. You get close, and they slip away again. Betelgeuse is 850 light years away, maybe 900. The distance changes depending on who you ask. But at 10 parsecs, it would dominate the sky. At 1 parsec, it would be 100 times brighter than that. At the distance of Alpha Centauri, 4 light years away, it would be brighter than Venus, brighter than anything in the night sky except the moon. And if it were where Alpha Centauri actually is, life on Earth would be different, maybe impossible. Maybe it wouldn't have started at all, but it's not. It's far enough away that we can look at it safely, far enough that its light is just light, not a threat. We see it as a dot, a red dot in Orion's shoulder, one of the brightest stars visible from Earth, but just a star. You don't get shadows from it, you can barely see it from a city. Distance saves us. In distance makes Betelgeuse beautiful instead of deadly. But this raises a question. Betelgeuse has swelled to nearly 1 billion times the Sun's volume. It radiates energy, like a furnace burning matter itself. It fills space in a way that erases the idea of empty orbits. And yet, it stops. It doesn't grow forever. It doesn't collapse into itself. It holds this size for thousands of years, balancing on the edge of something catastrophic. Why does Betelgeuse stop at this size? Why not bigger? Why doesn't Betelgeuse keep expanding forever? Why does anything stop growing? The answer applies to stars, but it starts with planets. Because planets have a size limit, a ceiling they can't break through no matter how much mass they gather, and that limit is smaller than you'd think. Jupiter is the largest planet in our solar system, at 318 times the mass of Earth, 86,881 miles across, 11 times Earth's diameter. You could fit 1,300 Earths inside Jupiter's volume. It's enormous, but it's also as large as a planet can get. At about 1.7 times Jupiter's mass, something strange happens. Planets stop growing outward, add more mass, and the diameter doesn't increase. The planet just gets denser, heavier, more compressed. It's like trying to inflate a balloon that's already full. You can keep pushing air in, but the balloon doesn't expand. It just gets harder and denser. Eventually, the rubber can't stretch anymore. That's electron degeneracy pressure. That's the wall planets hit. Picture this. If you stacked Earths on top of each other, you'd expect the pile to get taller. But after 1.7 Jupiter masses, the pile starts shrinking. The bottom Earths get crushed so hard that the atoms compress, and the whole stack becomes denser and smaller. Physics reverses your intuition. More mass means less size. This happens because gravity squeezes atoms closer together. The more mass you add, the stronger gravity pulls inward. At a certain point, electrons themselves resist being compressed further. They push back, not because of any force between them, but because quantum mechanics forbids two electrons from occupying the same state. It's a fundamental property of matter. Electron degeneracy pressure. The universe says no. One of the largest planets ever discovered is TRES 4b, 1.7 times Jupiter's mass, 1.8 times Jupiter's radius. It's right at the limit. But here's the strange part. TRES 4b has the density of balsa wood. It's so diffuse that you could crumple it like tissue paper if your hand were large enough. The planet is puffy because it orbits so close to its star that the star's radiation heats and inflates its atmosphere. It's not a solid object. It's a hot cloud held together by gravity, a balloon stretched to its breaking point. Keep adding mass beyond 1.7 Jupiter masses, and the planet doesn't just get denser, it becomes something else. At around 13 Jupiter masses, the core gets hot enough and dense enough for deuterium fusion to begin. Deuterium is heavy hydrogen, an extra neutron in the nucleus. It fuses at lower temperatures than normal hydrogen. The object starts glowing from internal heat. It's no longer a planet, it's a brown dwarf. A brown dwarf is like a fire that almost caught. Enough heat to glow, but not enough to sustain a flame. It fuses deuterium for a few million years, then fades. It's not a star. It's a planetary furnace that ran out of fuel before it even started. Too massive to be a planet, not massive enough for sustained hydrogen fusion. It sits in between, a failed star. At around 80 Jupiter masses, hydrogen fusion begins. The core reaches 10 million degrees. Protons slam together with enough force to overcome their electromagnetic repulsion. They fuse into helium, releasing energy. The object becomes a true star. It can burn for billions of years. It has crossed the threshold. It's no longer failed. It's alive. This means planets have a ceiling, 1.7 Jupiter masses. Beyond that, you're building something different. You're climbing a ladder towards stars. Brown dwarfs are the middle rung. Stars are the top. But planets can't reach either. They stop at the first step. The universe sorts objects by mass. Planets below 13 Jupiter masses. Brown dwarfs between 13 and 80. Stars above 80. Clean categories. Clear boundaries. But the boundaries aren't arbitrary. They're written into the physics of fusion and compression. The universe decides what something is based on what happens in its core. This is why we don't find planets the size of stars. It's not that they haven't formed yet, it's that they can't form. Gravity won't allow it. Add enough mass to make something star-sized, and you've made a star. The heat, the pressure, the fusion, all of it follows. Size and type are linked. You can't have one without the other. And even Jupiter, the king of planets in our system, is at the mercy of this limit. If you could somehow add more gas to Jupiter's atmosphere, more hydrogen and helium, you wouldn't make it bigger. You'd make it denser, smaller even. The extra mass would pull everything inward. The core would compress. The radius would shrink. You'd be building backward. Think about that. There's a point where adding material makes an object smaller. It defies every intuition you have about construction. But it's real. It's measurable. We've observed it in exoplanets across the galaxy. Planets near the 1.7 Jupiter mass limit all have similar radii. They've hit the ceiling. They can't grow outward anymore. This ceiling explains why the search for the largest planet in the universe has an endpoint. There's a maximum size. Roughly 1.8 times Jupiter's radius for the puffiest, lowest density planets. For most planets, the limit is closer to 1.2 or 1.3 Jupiter radii. That's it. That's as big as they get. Not because we haven't found bigger ones, because bigger ones don't exist. Planets are boxed in, constrained by quantum mechanics and gravity. They can't shrink below a certain size without losing their atmosphere. They can't grow beyond a certain size without becoming something else. They occupy a narrow band of possible existence, and within that band, they're diverse. Rocky planets, gas giants, ice giants, hot Jupiters, but all of them are limited. All of them stop growing, which brings us back to stars. Stars don't have the same ceiling. They can grow as large as physics allows. Betelgeuse is 800 times the diameter of the Sun. Other stars are even larger. UY Scuti, Stevenson, 2-18, giants that dwarf our Sun, but they're not planets. They're fusion reactors. They obey different rules. But what happens when a star does become something else? What's left after the explosion? What's left after a supernova? The explosion itself is spectacular, violent, brief. A star tears itself apart and throws most of its mass into space. But the core remains. What's left behind depends entirely on how massive the star was to begin with. Low-mass stars leave white dwarfs. Medium-mass stars leave neutron stars. Massive stars leave black holes. 3 possible endpoints, 3 entirely different objects. Let's start with white dwarfs. And these are the remnants of stars up to about 8 times the mass of the Sun. When these stars exhaust their fuel, they shed their outer layers and leave behind a dense core. The core doesn't collapse all the way. It's held up by something called electron degeneracy pressure. That's a quantum mechanical effect. Electrons refuse to occupy the same space. They push back against gravity. The result is a white dwarf, an object roughly the size of Earth, but containing the mass of an entire star. The density is difficult to comprehend. A teaspoon of white dwarf material weighs about 5 tons. That's as much as an elephant. An entire elephant compressed into a teaspoon. The atoms are crushed together. The space between electrons and nuclei is gone. What was once a star the size of the Sun is now the size of our planet. Sirius B is a white dwarf. It orbits Sirius, the brightest star in our night sky. You can't see it with the naked eye. It's too dim, but it's there. A dead star, cooling slowly in the darkness. White dwarfs don't do much. They just sit there, radiating away their residual heat over billions of years. Eventually, they'll cool to the temperature of the surrounding space. They'll become black dwarfs, invisible, silent. The universe isn't old enough yet for any black dwarfs to exist, but given enough time, every white dwarf will fade to nothing. That's the fate of most stars. Our Sun will become a white dwarf. In about 5 billion years, it will swell into a red giant, shed its outer layers, and leave behind a dense core. That core will be the size of Earth. It will glow faintly for trillions of years. Then it will go dark. But Betelgeuse won't become a white dwarf. It's too massive. Stars between roughly 8 and 20 solar masses don't stop at electron degeneracy pressure. When their cores collapse, the pressure is so immense that electrons are forced into protons. They combine. They become neutrons. The core becomes a single, giant atomic nucleus, a neutron star. Neutron stars are where things get extreme. They're about 12 miles in diameter. 12 miles. That's the width of a small city, but they contain between 1.4 and 2 solar masses, an entire star compressed into something the size of Manhattan. The density is beyond anything we experience in daily life. A teaspoon of neutron star material weighs 10 million tons. Not 5 tons like a white dwarf, 10 million tons. That's as much as 10,000 aircraft carriers. 10,000 in a teaspoon. It's not just dense, it's compressed beyond what normal matter can withstand. The neutrons are packed so tightly that they're almost touching. There's no space between them. Gravity has crushed the atoms out of existence. What remains is pure neutron matter, a state of matter that doesn't exist anywhere else in the universe except inside neutron stars, and possibly the cores of black holes. Neutron stars spin fast. Some of them rotate up to 700 times per second. 700. A point on the equator of one of these stars moves at 20% the speed of light. If you stood on the surface, which would instantly kill you, you'd experience a sunrise every 1.4 milliseconds. The star would blur. You couldn't see individual rotations. It would just be a smear of light. A day and night would flicker past faster than your brain could process. The entire sky would become a continuous band of light. These rapidly spinning neutron stars are called pulsars. They emit beams of radiation from their magnetic poles. As they spin, the beams sweep across space like a lighthouse. If the beam points toward Earth, we see a pulse. Regular, precise. The first pulsar discovered was thought to be an alien signal. It pulsed every 1.3 seconds, perfectly regular. Scientists called it LGM-1, Little Green Men-1. They were half serious. It turned out to be a neutron star, not aliens, just the corpse of a massive star, spinning in the dark. Neutron stars have mountains. This is the part that gets me. Irregularities in their crust that rise about 5 millimeters above the surface. 5 millimeters. And that doesn't sound like much. You wouldn't trip over a 5 millimeter bump, but the gravitational binding energy of a neutron star is so immense that a 5 millimeter mountain contains more energy than the most powerful nuclear bomb ever detonated. The mountains are tiny, but they're held down by gravity so strong that they warp space-time. The crust itself is made of iron nuclei packed into a crystalline lattice. It's the hardest material in the universe, billions of times stronger than steel, and even that crust can barely withstand the pressure. When Betelgeuse explodes, its core will collapse from the size of Earth to the size of Manhattan in 0.25 seconds, a quarter of a second. The collapse releases more energy in that quarter second than the sun will emit in its entire 10 billion year lifetime. And most of that energy goes into neutrinos. They pass through the outer layers of the star and escape into space. A tiny fraction of the energy drives the explosion. The core bounces. Neutron degeneracy pressure stops the collapse. The result is a neutron star. Unless it doesn't stop. If the core is too massive, even neutron degeneracy pressure can't hold it up. The collapse continues. The core shrinks past the neutron star limit. It crosses a boundary called the event horizon. Beyond that point, nothing escapes. Not light, not matter, not information. The core becomes a black hole. Black holes are remnants of stars above roughly 20 solar masses. Nothing can support the collapse. Gravity wins completely. The matter doesn't stop at any particular density. It just keeps collapsing. According to general relativity, it collapses to a point of infinite density, a singularity. We don't know if that's physically accurate. Quantum mechanics probably intervenes at some scale, but we don't have a theory that describes what happens. The math breaks down. All we know is that beyond the event horizon, the laws of physics as we understand them stop making sense. The event horizon is the boundary, the point of no return. If you cross it, you can't come back. Not because you lack fuel or speed, because space-time itself is structured such that all paths lead inward. There's no direction that points out. It's not a physical barrier. It's a geometric property of curved space-time. Once you're inside, the singularity is in your future, not your space. Your future. You will reach it the same way you will reach next Tuesday, inevitably. Betelgeuse is roughly 18 to 20 solar masses. It's right on the boundary, the edge between neutron star and black hole. If the core retains just a bit more mass during the collapse, it becomes a black hole. If it sheds enough mass in the explosion, it becomes a neutron star. The difference is razor thin, a matter of a solar mass or two. We won't know which one it becomes until it happens. When the supernova occurs, we'll see the explosion, the light show, the brightening, but we won't immediately know what's left behind. The remnant will be buried in the expanding debris. It will take years, maybe decades, for the cloud to clear enough for us to observe the core. Only then will we know. Neutron star or black hole, a spinning lighthouse or a void in space-time. Both are extraordinary. Both are endpoints. But they're fundamentally different. One is matter at its breaking point. The other is matter that broke. The universe creates these objects constantly. Somewhere in the observable universe, a star is collapsing right now. Another neutron star, another black hole. They're not rare. There are an estimated 100 million neutron stars in the Milky Way alone. Black holes number in the tens of millions. Most of them are invisible, silent. We only detect them when they interact with something else, when they pull matter from a companion star, when they merge with another black hole, when they consume gas and emit X-rays. Otherwise, they're just there, invisible anchors in the fabric of space-time. Betelgeuse will join them. One more remnant, one more endpoint. But what will we see when it happens? But what does a supernova look like from Earth? What will we see when it happens? That's the question. Betelgeuse is enormous. It's dying. It will explode. But what does that actually look like from Earth? The supernova will reach a magnitude of -12. That's an astronomer's way of measuring brightness. The full moon sits at -12.6. Betelgeuse's supernova will be almost as bright as the full moon. Not a pinpoint of light, not a star, something else entirely. When Betelgeuse explodes, it will be bright enough to cast shadows at midnight. You'll be able to read a book by its light. It won't be a star. It will be a second sun, hanging in Orion's shoulder, visible for months. You'll walk outside at night, and the ground will have two shadows, one from the moon, one from a dead star 500 light-years away. It will be visible during the day for weeks. You'll look up at the blue sky and see it, a bright point competing with the sun. That's never happened in modern history. Not once. No supernova has been visible in daylight since the invention of the telescope. At night, it will dominate the sky, brighter than Venus, brighter than Jupiter, second only to the moon. It will stay that bright for weeks, maybe months. Then it will begin to fade, slowly at first, then faster. Over the course of months, it will dim from a second sun to a bright star, then to a faint glow, then nothing. The whole event, from explosion to invisibility, will take about a year, maybe longer. You'll watch it happen in real time. A star dying across your entire lifespan compressed into 12 months. This isn't speculation. We've seen it before. Supernovae have appeared in our sky throughout history. People recorded them, wondered about them, built myths around them. In 1054, a supernova appeared in the constellation Taurus. Chinese astronomers called it a guest star. It was visible during the day for 23 days. At night, it outshone everything except the moon. Native Americans carved petroglyphs of it. The light from that explosion created the Crab Nebula. We can still see the remnant today, nearly 1,000 years later. In 1572, another supernova appeared. Tycho Brahe observed it. He measured its position night after night. It didn't move relative to the stars. That was shocking. At the time, most people believed the heavens were unchanging, perfect, eternal. Tycho's supernova proved otherwise. The sky could change. Stars could die. The supernova was visible for 16 months. The light left that star just as Copernicus published his heliocentric model. By the time the supernova faded, Shakespeare was 8 years old. That's how long a supernova lasts. Long enough to watch a generation grow. In 1604, Johannes Kepler observed the last supernova visible in the Milky Way. It appeared in the constellation Ophiuchus, bright enough to be seen during the day, visible at night for over a year. Then it faded. We haven't seen one since. Not in our galaxy, not in 420 years. Supernovae happen regularly. The Milky Way produces about 2 to 3 per century, but most are obscured. Dust blocks the light. The explosion happens on the far side of the galaxy, hidden behind billions of stars. We don't see them. We only detect them later, with telescopes, in other wavelengths. X-rays, infrared. The visible light never reaches us. Betelgeuse is different. It's close, only 500 light-years away, and it's right there, in one of the most recognizable constellations in the sky. Orion is visible from almost everywhere on Earth. When Betelgeuse explodes, everyone will see it. Every human on the planet. No matter where you are, no telescope required, just look up. At 500 light-years, it's far enough to be safe. The explosion will be brilliant, but it won't harm us. Supernovae release gamma-ray bursts, high-energy radiation that can strip atmospheres from planets. But gamma rays weaken with distance. By the time they reach Earth, they'll be harmless. Yet we'll get the light show without the danger. There's something unsettling about that 500 light-year distance. The light from Betelgeuse that we see tonight left during the Renaissance. Around 1524, Magellan was circumnavigating the globe. The Aztec Empire was falling. Copernicus was developing his model of the solar system. The light from that moment is reaching us now, 5 centuries later. If Betelgeuse exploded tomorrow, we wouldn't see it for another 500 years. The explosion could be happening right now, in real time, and we'd have no idea. We're always looking at the past. Every star in the sky is a time capsule. The farther away it is, the older the light. That means there's a chance Betelgeuse has already exploded. A real chance. Not likely, but possible. If it went supernova in the year 1524, right when Magellan was sailing around the world, the light is traveling toward us right now. It will arrive within our lifetime. We could wake up one morning, look at Orion, and see two bright stars where there used to be one, Rigel and a brilliant new point of light. The supernova would be breaking news. Every telescope on Earth would turn toward it. Every astronomer would scramble to observe, and the explosion itself would be 500 years old. The light would have been traveling through space since the Renaissance, finally arriving in the 21st century. We don't know when it will happen. That's the honest answer. Betelgeuse could explode tonight, or 1,000 years from now. Or it could have already exploded, and we're just waiting for the light to arrive. Astronomy is patient. The universe operates on timescales that make human lifetimes irrelevant, but this one might happen while we're here, while we're watching. That's rare. Supernovae in our galaxy, visible to the naked eye, happen maybe once every few centuries. The last one was in 1604. We're overdue. It would be the astronomical event of the millennium. A supernova in our cosmic backyard, brighter than anything in the night sky except the moon. Visible for months, changing the shape of Orion forever. People would talk about it for generations. Where were you when Betelgeuse exploded? What did it look like from your part of the world? Did you see it during the day? Did you read by its light at night? The universe doesn't often give us moments like that, events we can witness with our own eyes. And most of what happens in space is invisible, too faint, too far, too slow. But a supernova 500 light years away? That's close enough to see, close enough to matter, close enough to remember. Betelgeuse sits in the night sky, red and flickering. We watch it, we measure it, we wait. Somewhere in the void between us, light is traveling. Maybe it's the light of an ordinary red supergiant, still burning. Or maybe it's the light of an explosion, a star torn apart by its own gravity, a supernova brighter than 1 billion suns. We won't know until it gets here. But Betelgeuse isn't unique. There are other stars like it, massive, unstable, nearing the end, and some that are even larger. Betelgeuse is vast, a star that dwarfs our sun, swollen to the edges of its own solar system. But it's not the largest, not even close. There are stars out there that make Betelgeuse look ordinary, stars so large they defy every intuition you have about what a star can be. We call them hypergiants, and they exist at the very edge of what physics allows. Take UY Scuti. For years, it held the record as the largest known star. Its diameter is roughly 1,700 times wider than the Sun. That's 1.2 billion miles across. If you replaced our Sun with UY Scuti, its surface would stretch past Jupiter's orbit. Everything inside would be gone. Mercury, Venus, Earth, Mars, Jupiter, all swallowed by a single star. But UY Scuti no longer holds the record. That title, at least for now, belongs to Stephenson 2-18, a red hypergiant in a distant star cluster so large it challenges our ability to comprehend scale. Its diameter is roughly 2,150 times the Sun's, 1.5 billion miles across. Picture this. If you placed Stephenson 2-18 where our Sun sits, its surface would reach past Saturn's orbit. Earth would be deep inside, vaporized instantly. Mars, gone. Jupiter, engulfed completely. Saturn would be skimming the outer layers of the star itself, its rings melting into plasma. The entire inner solar system would simply cease to exist, erased by a single burning sphere. Think about that for a second. There's also Westerlund 1-26, another hypergiant, another contender. Its diameter sits around 1,500 solar radii, slightly smaller than the others, but still impossibly vast, still large enough to hold billions of Earths inside its volume. All of these stars are red supergiants. All of them are near the end of their lives, and all of them will explode as supernovae within the next 1,000,000 years. In cosmic terms, that's practically tomorrow. They're already dying. We're just watching the final act. But here's the problem. Measuring these stars is almost impossible. When we say a star has a diameter of 2,000 times the Sun, that number comes with enormous uncertainty. These hypergiants don't have sharp edges. Their outer layers are so diffuse, so spread out, that they blur into the vacuum of space. Trying to measure the diameter of a hypergiant is like trying to measure the edge of a cloud. Where does the cloud end and the sky begin? There's no clear boundary, just a gradual fade from something into nothing. The stars themselves don't help. They pulsate, and their outer layers expand and contract over months or years. The diameter changes depending on when you measure it, and the light we observe gets distorted by dust, by gas, by the star's own atmosphere. We're trying to measure something 1,000 light years away that doesn't have a defined edge and keeps changing size. So the numbers are estimates, educated guesses based on brightness, temperature, distance. We use models, we make assumptions, and sometimes those assumptions turn out to be wrong. That's why the record keeps changing. UY Scuti was the largest. Then better measurements showed it was smaller than we thought. Stevenson 2-18 took the title, but even that's provisional. There are other candidates we can't measure accurately yet. Stars too distant, too obscured by dust, too uncertain. The largest star in the universe might be out there right now, shining in some corner of the galaxy we haven't surveyed carefully. We just can't see it well enough to confirm. The record isn't settled, it's waiting. Every time we build a better telescope, every time we refine our techniques, the answer changes, and it will keep changing. Because we're not just measuring stars, we're measuring the limits of what we can observe, and those limits are always shifting. These hypergiants are rare. We've only found a handful in the entire Milky Way. Out of hundreds of billions of stars, maybe a dozen are this large. They live fast and die young, just a few million years from birth to supernova. By the time we discover one, it's already ancient, already in its final act, already doomed. They burn so hot, so bright, that they consume their fuel at a staggering rate. A star like the Sun will shine for 10 billion years. A hypergiant gets a few million, maybe less. It's the price of being that large. The bigger you are, the faster you burn, the faster you die. And when they go, they don't fade quietly. They explode. They seed the galaxy with heavy elements. They trigger new waves of star formation. They leave behind neutron stars or black holes. Their deaths are as spectacular as their lives. But we're still finding them, still measuring them, still arguing about which one deserves the title. The universe doesn't care what we find convenient. It doesn't give us clean answers or sharp boundaries. It gives us clouds of plasma 1 billion miles wide, pulsating and flickering at the edge of existence. Somewhere out there, hidden by distance or dust, there might be a star even larger than Stevenson 2-18, a hypergiant we haven't spotted yet, or one we've seen but can't measure. The largest star in the universe isn't a settled fact. It's a question we're still trying to answer, and maybe that's the point. The universe still has secrets, still has mysteries we haven't unraveled. We look out into the dark and we find giants, but we also find limits, the edges of what we can know, the boundaries of what physics allows. But focusing on size misses something important. The question isn't just how big, it's why. Why do we care about the largest anything, the biggest star, the tallest mountain, the longest river? There's something in us that wants to know the extremes. But size is just one axis, just one way to measure a thing. Now, the universe doesn't think in terms of diameter. It thinks in terms of mass and density and energy and time. Take a neutron star, 12 miles wide, small enough to fit inside a city. You could drive across it in 20 minutes, but it contains more mass than Betelgeuse's core, a star that's 1,000 times larger, packed into something you could see from one edge to the other. Size is deceptive. A neutron star weighs as much as the Sun, compressed into a sphere the size of Manhattan. The universe doesn't care how big something looks. It cares how much it weighs, how dense it is. A black hole is even more extreme. The singularity at the center is infinitely dense. All the mass collapsed into a point with no volume. The event horizon around it might only be a few miles wide, smaller than some asteroids. Oh, but it contains the mass of dozens of suns. The largest stars in the universe are diffuse, spread out. Their outer layers are almost a vacuum. A black hole is the opposite, everything crushed into nothing. Asking what's the largest star is like asking what's the tallest mountain on a planet where the ground is constantly shifting. The answer changes depending on when you ask and how you measure. Stevenson, 2-18 might be the biggest now, but it's pulsating, expanding and contracting. In a few thousand years it might be smaller, or it might have exploded. The title of largest star isn't permanent. It's a snapshot, a moment in time. The largest stars are also the shortest lived. Hypergiants last only a few million years. They burn so hot and so fast that they tear themselves apart. Small red dwarfs can live for trillions of years, longer than the current age of the universe. They sip their fuel slowly. They'll still be burning long after every giant has died. Size comes at a cost. The bigger you are, the faster you burn out. The Sun is a medium-sized star, not particularly large, not particularly small, yellow dwarf, average. But the Sun is more typical than Betelgeuse or any hypergiant. Most stars are smaller than the Sun, dimmer, cooler. The universe isn't made of giants, it's made of the ordinary, the unremarkable. Here's the surprise. The most common stars in the universe are red dwarfs, small, dim, incredibly long-lived. They make up 70% of all stars. 70%. Betelgeuse and the hypergiants are cosmic celebrities, outliers, rare exceptions. And the universe is mostly made of stars you've never heard of. Stars so dim, they're invisible to the naked eye. You can't see them without a telescope, but they're everywhere. The largest planet or the largest star is a curiosity, not the norm. The universe is defined by the ordinary, not the extreme. We obsess over the largest because humans think in terms of size, but the universe thinks in terms of energy, gravity, and time. Betelgeuse is impressive, 1 billion miles wide, but a pulsar spinning 700 times per second is more extreme. A tablespoon of neutron star material weighs 1 billion tons. That's more extreme than any bloated hypergiant. We're just bad at seeing it. We see what's big and bright. We miss what's dense and powerful. I think about this sometimes. Why we're drawn to the biggest, the fastest, the brightest. And maybe it's because we're small and we want to prove we can comprehend the large. Maybe it's because size is easy to visualize. You can picture something 1,000 times wider than the Sun. You can't picture infinite density. You can't picture a trillion-year lifespan. So we focus on what we can grasp. Size is a product of mass, age, and composition. It's not a fundamental property. A star doesn't decide to be large. It's large because it has a lot of mass, and it's at a certain stage in its life. Betelgeuse is huge because it's dying. Its core is collapsing. Its outer layers are expanding. Give it a few 100,000 years, and it won't be large anymore. It'll be a neutron star, 12 miles wide, or a black hole, even smaller. The question isn't just how big, it's why. Why does a star get that large? What does that tell us about its mass, its age, its future? The largest stars show us the upper limits of what's possible, the edge of the range. But they're not the full story. They're one data point, one extreme on a spectrum that stretches from red dwarfs to hypergiants, from neutron stars to supermassive black holes. The universe is vast, but it's also dense. It's also ancient. It's also fleeting. Size is just one way to measure it. Mass matters, density matters, lifespan matters, energy output matters. The largest star in the universe might not be the most massive. It might not be the most luminous. It might not be the most extreme. It's just the largest, and that's worth knowing. But it's not the only thing worth knowing. Maybe the extremes matter, because they show us the edges of what's possible. Yes, or the boundaries that physics allows. The largest star tells us how big a star can get before it tears itself apart. The smallest star tells us how little mass you need before fusion stops. The oldest star tells us how long the universe has been around. The extremes define the range, and somewhere in that range, the universe unfolds. We started this journey by talking about light, photons leaving Betelgeuse 500 years ago, traveling through the void, finally reaching Earth. Those photons are still arriving. Right now, as you watch this, ancient light from a dying star is hitting telescopes, hitting your eyes if you look up on a clear winter night. That light is a message from the past, a snapshot of a star that might already be gone. The largest stars we've found, Betelgeuse, Stephenson 218, all the hypergiants scattered across the galaxy, they show us one thing clearly. The universe has edges, boundaries, limits to what's possible before physics steps in and says, no further. A star can only get so large before radiation pressure tears it apart. It can only burn so hot before it exhausts its fuel in a cosmic blink. These extremes define the range. Yet from the smallest red dwarfs at 8/100ths of a solar mass to the largest hypergiants at 250 solar masses. That's the spectrum. That's what the universe allows. Think of it like a mountain range. The largest stars are the peaks, visible from a distance, dramatic, rare. They catch the light, they dominate the skyline, and everyone points at them. But the range itself is made of millions of smaller hills, ordinary mountains, ordinary slopes. The sun is one of those hills, not a peak, not a valley, just somewhere in the middle, unremarkable by every cosmic measure. And we live on a grain of sand on that hill. Betelgeuse is a peak, the sun is a hill, and yet, here we are. There's something quietly profound about that. We don't orbit the largest star. We don't orbit the brightest, or the most massive, or the most extreme. We orbit a middle-aged, medium-sized yellow dwarf in a typical spiral galaxy. We are cosmically ordinary, and maybe that's the point. Maybe life doesn't need extremes. Maybe it needs the unremarkable, the steady, the boring, the stars that burn for billions of years instead of millions. If you could watch the universe in fast forward, the hypergiants would flicker and die like camera flashes. Bright, brief, gone. The red dwarfs would glow steadily for trillions of years, longer than the current age of the universe, longer than galaxies will keep their spiral arms. The extremes are spectacles. The ordinary is what lasts. We exist in the ordinary. We are made of the ordinary. And somehow, from this grain of sand on an unremarkable hill, we've measured the peaks. The photons from Betelgeuse that we discussed at the beginning, the ones that left 500 years ago, when the printing press was new and most of the world had never seen a map, they're still traveling. They'll keep traveling. And when Betelgeuse finally explodes, when it goes supernova in some distant century or millennium, new photons will begin the journey. They'll take 500 years to get here. They'll arrive long after we're gone, and someone else will look up and see a bright star where Betelgeuse used to be. The light will be old, but the sense of wonder will be new. That continuity matters. The universe keeps unfolding. We're just here for a moment, watching. Here's the thing though, the largest star in the universe isn't Betelgeuse. It isn't Stephenson 218. It isn't any star we've found. Yet it's the one we haven't discovered yet, the one waiting at the edge of our instruments, too far or too faint to see. The record will be broken again. Someone will point a telescope at a distant cluster and find something even larger, even more extreme. And that's the point. The search never ends. There's always something larger, stranger, more impossible. And we'll keep looking. Not because we need to find it, because we need to look. The universe is vast. We are small. We're standing on a rock, circling a medium star in one galaxy among hundreds of billions. We are unremarkable by every measure. And yet, here we are, looking up, asking questions, measuring the immeasurable, building instruments to see farther, deeper, older. We've mapped the edges of what's possible. We've found the largest stars, the smallest stars, and the oldest light. We've traced the boundaries that physics allows, and we did it from a grain of sand on an ordinary hill. If you enjoyed this exploration, consider subscribing. There are more journeys like this one, more questions, more edges to find. The universe contains everything, the extremes and the ordinary, the peaks and the hills, the hypergiants that live for millions of years and the red dwarfs that will outlive galaxies. And somewhere in that range, on an unremarkable planet circling an unremarkable star, life emerged, looked up, and started measuring. That's enough.